All right, guys, so let's go ahead and get started here. So you've had a chance to look at these two equations, and I'm just going to choose the first three people on my screen, which is Hiram, Mikkel, Brandon. There are three transformations going on here. I want you to tell me those. Before you do, let's actually get our parent function here. So it's good to talk about our parent function. So actually, Hiram, I'm going to have you talk about the parent function, and then Kimberly, you're going to take one of the transformations. Okay. Hiram, what is our parent function going to be on this first problem? Meaning, if I can't hear you, I think you're muted.
E to the x.
Awesome. Now, what is the value of E? If I just look at plain old E, that's the Sesame Street number of the letter. Yeah, number of the day. That's confusing little kids out there. What is the value of E, Hiram? You're still muted. I see your
I
lips.
keep forgetting. And 2.718.
So is that going to be exponential growth or exponential decay?
Growth.
Yes, good job. How did you know that?
Because it increases in y value.
Another way to look at that is it's bigger than 1. Okay, if your base is bigger than 1, it's going to be growth.
Yeah.
And 2.718 is bigger than 1, so we're good. Awesome. Okay, so Mikkel, tell me one transformation that's going on here.
Well, the 2 tells us that it's being stretched by a factor of 2.
Awesome. And in which direction is that being stretched by a factor of 2?
Vertically.
Awesome. So that's a vertical stretch. Our y values are being stretched. Awesome. Brandon, can you tell me another thing that's happening with f of x here to our parent function?
Is it a shift to the right?
Not to the right. It'd have to be up in the exponent to be right. But if it's on the outside, then what will that plus 1 do?
Oh no, it'll. What's it called? I don't know what the word is. I'm trying to think of what it means. It'll go up, right? Yeah.
There you go. Yeah, I think the technical word is that it's a vertical translation, but I just
translation.
shift up. You don't have to worry about being too precise here. So yeah, it just shifts it up 1. All right, cool. Thanks, Brandon. Kimberly, last one. We've just got this negative, and it's up in the exponent. What is that going to do, Kimberly?
Flip it across the y-axis.
Nice job. So if it's on the outside, it's x, but on the inside, it is y. All right, cool. That's exponentials. Now, I'm just going to ask for a volunteer on g of x, because it's really not that hard, but I don't want to put anyone on the spot too much. So someone unmute yourself and tell me, what will the limit to growth? In other words, the carrying capacity. What is that going to be here for g of x?
Isn't it 9?
It is 9. Thank you. I think that was Kimberly. I'm not sure, but I think it was. So yeah, whatever the numerator is, that's your limit to growth. That's pretty easy. Now to get the y-intercept, what we're going to do is we're going to plug in 0. And again, when you look at the formula here, it looks pretty scary, but it's really not too bad. So what I'm going to do is I'm going to plug in 0 for the x. And when I do, that's going to give me e to the 0, which any number to the 0 just turns into 1. So this becomes 9 over 1 plus 2, which ends up being 3. And 9 over 3 is just 3. So this logistic function here, although it looks scary, is pretty easy. We're just going to have 2 horizontal asymptotes, one at 0, and then one at our limit to growth, or our carrying capacity, which is 9. And we're going to have a y-intercept at 3. And so if I change colors here, if I were to graph this thing, it's going to look like this. It's going to go through 3, and it looks something like that. If you want to check it, just go on to Desmos. All right, that was a quick review of what we learned last time, the basics of exponential growth and decay, as well as logistics. Now, if you have questions, hang on to those till the end. I'm going to do some review after our lesson today so we don't run out of time, but we won't because it's going to be a pretty quick lesson. And then make sure you have a graphing calculator or Desmos pulled up. Okay, so now what we're going to do today is we're going to take those logistic and exponential functions and we're going to model them in real life situations, right? Just what you wanted on a Monday morning. Now, just a couple reminders. Number one, remember we have those weekly progress reports. Week 4 is due today, so if you didn't do it Friday or Saturday or Sunday, you could still do it today. I am recorded, so we're good there. Now, today is Monday, and it is a B day because we switched it. And tomorrow, Tuesday, is an A day. Now, when we come back from Thanksgiving break, Monday, November 30th, is an A day. So now you're going to have 2 A days in a row. And then the Tuesday is a B day. Now, that B day, December 1st, we're going to have a quiz, but also this is when your parent projects are due, the parent function projects are due. So make sure you guys get those wrapped up. You had like a 2-week extension because those were supposed to be due last week, but we're on whatever, okay? Hopefully we'll be able to actually come back next week. I've got my fingers crossed so we don't have to do this online stuff. So do you have any question on things that are due before we get started? Anybody, any questions? All right, so yeah, just make sure your parent function projects are awesome and you turn them in. If you did an electronic version, you can just turn them in through Canvas and always just email me if you have questions. All right, so modeling, what that basically means is we are going to take real life situations and try to create a graph that models what's going on so we can try to figure some things out about it, okay? Now, this formula right here is going to be our best friend for this lesson, okay? So I'm going to highlight it and some key information here. So this is a formula. You need to write that down somewhere in your notes. Now, this is, let's talk about the different variables here. So P is your population. That's what P stands for. And it's changing at a percentage rate called R. So this value R in there, that is your percentage rate. Now we're talking about each year. So when we're talking about T is time in years. R is your rate. And I'm going to highlight that part and underline it too. It needs to be written as a decimal. What that means is if I'm told the percentage rate is 5%, I need to change that to 0.05 when I put it in. Okay, and then last piece of information here, P sub 0. Oh, sorry, I didn't want the pen. P sub 0 means initial population. It's your population at time 0. Okay? All right, now some other key information here. If your rate is greater than 0, then it's going to make it so the base is bigger than 1, which means you have exponential growth. And that's going to be called your growth factor. If you look at 1 plus R, that's going to be your growth factor. So there's going to be 2 things that's going to ask for. One might be a growth factor, which includes the 1, and then the other one is just going to be the rate, which doesn't include 1. Okay? Then there's going to be, on the other hand, if R is less than 0, then that means 1 plus R is less than 1, which means we've got exponential decay. It's going down. And we're going to call the 1 plus R your decay factor. So just kind of building off of what we learned last time, if the base is bigger than 1, it's growth. If the base is less than 1, it's decay. And that's all going to be determined by your percentage rate. Let's look at 2 easy examples of this, okay? All right, so here what we have are 2 population models represented as exponential growth or decay. One is for San Jose and one is for Detroit. And what we need to do is we need to figure out, does it represent growth or does it represent decay? And then find the percentage rate, whether it's growth or decay. All right, so to do that, let's just look at A. I'm going to do A for you, and then I'll let you look at B. So I'm looking at San Jose, my old friend. I'm looking at the base here and I'm saying, is the base bigger than 1? And sure enough, the base is 1.0064. 1.0064 just barely is bigger than 1, but it's still bigger, so this would be an example of exponential growth. Now, how do I get to 1.0064? If you look at your formula, the base is 1 plus your rate. So what will your rate be? It's going to be 1 plus 0.0064. Now, that 0.0064 is written, as I call the decimal. It's not a percentage yet. If I want to change that to a percentage, I need to move that decimal 2 to the right. What that tells me is that that percentage rate, that rate of growth, is going to be 0.64%. So in San Jose, the population is increasing at a rate of 0.64. All right, that's how you do that. That's all it's asking for. Is it growth? Is it decay? And then what is the growth or the decay rate? Now, what I want you guys to do is I want you to look at Detroit. And I want you to figure out, is it growth or decay? And what is a growth or decay rate? I'm going to give you about 30 seconds, and then I'm going to call on someone. So 30 seconds, go. All right, that was 30. Hey, Chloe, do you think you could help me out on this one?
Yeah.
Awesome. What did you say? Is it growth or decay, and why?
Decay because it's less than 1.
You were spot on. So 0.9858 is less than 1, so this is DK Donkey Kong. No. If you guys haven't played DK 64, you should go back. It was a great game, DK like this. Okay. Now, Chloe, what about the DK rate? Were you able to figure that out? And if so, how did you get it?
No, I couldn't figure it out.
Okay, that's all right. Is there someone out there who could explain how they got it? Or do you want me to do it? I think that means you want me to do it. All right. So,
I
kind of
think
like,
I got it.
yes, thanks, Mikkel. Go ahead.
So I'm not sure if I did it right, but I subtracted 0.9858 from 1 and got 0.0142. So would that be a point 1.42% decay?
That sounds spot on. Let me write this out. So people are like, how'd you get that? Well, if we're looking, come back here with me. We're looking at 1 plus r, right? Gave us 0.9858, right? So then if I subtract the 1 over, I get this guy right here, that our decay rate must have been that. And it will show up as a negative, which means, there we go. But yeah, so this means our decay rate is 0.0142, which means, as Mikkel said, move that over, it's going down at a rate of 1.42%. So its population is decreasing. Awesome. Well done, Mikkel. Do you guys have any questions on that? If you do, just shout it out, but I'm going to keep on rolling. All right, so let's go to this next problem here, okay? So determine the exponential function with initial value 12 increasing at a rate of 8% per year. All right, all we're going to do on that, guys, is we are going to take our formula. We said P of t is equal to p sub 0, 1 plus r, and then raise it to the t. Now, this is a function in terms of t. We're used to seeing like f of x. It's a function in terms of x. This is a function in terms of time. So t is going to be our variable. And we're just going to plug the other things in where they belong. So what I'm told here is that the initial value is 12. That means p sub 0, remember that's your initial population, it's going to be 12. And then it's increasing at a rate of 8%. Now, this is where people might mess up here is they might put 8 right there. And oh, we can't do that. We got to change it to a decimal. So someone shout out, what should I put in there instead of 8?
Is it 0.08? Sorry.
Yes, awesome. I think I got like 3 people at the same time. Thanks, guys, for participating. And you were spot on. So P of t is going to be 12. And when I do 1 plus 0.08, I'm going to get 1.08, and that's raised to the t. So if I said, hey, so it started out at 12 people and it's increasing at 8%, how many people will there be in like 20 years? I just plug in 20 for t, and then I put that in my calculator, and boom, that's how many people our model is predicting there to be in 20 years. Now, granted, our model won't be exact, but it can kind of give us an idea of what to expect. All right, thanks, guys. Let's keep going. So now, let's talk about this one. So now it's going to get a little more complicated, but nothing too crazy. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict the number of bacteria. Predict when the number of bacteria will be 3,500. No, 350,000. There we go. Now, this is really kind of a two-part question. Part one, we need to come up with an equation that models what's going on here, okay? Part two, and sorry, that says equation. My handwriting is not on today. Equation, there we go. Part two, what we're going to do is we are going to then make that prediction based on our model. So I'm going to go through this and I'm going to highlight any key information we need to know. For example, suppose a culture of 100 bacteria. What is that 100 bacteria going to represent? That's our initial population. Now, we're told that this doubles every hour. What does that mean our rate is going to be if it's doubling every hour? Well,
Is it squared?
is it squared? Is that what you said, Josh?
Yeah.
That's a good guess, but squaring isn't going to double it every hour. But if we have a base of 2, that's how we double it every hour. So good guess, and you're close. But it's going to be, we're going to make the rate be 200%. That means we're doubling it. Now, if you're like, I don't get that. Well, let's just talk about it, okay? If we start with 100 and it doubles every hour, that means in 1 hour, I will have 200, right? Now, what we want to figure out is what is our rate going to be. So we're going to have 1 plus r, and that's going to be raised to our time. Well, we said it doubles every 1 hour, right? So our time will be 1. So now what that means here, guys, is we just want to solve for r here. So I'm going to first divide by 100. And 200 divided by 100 is 2. Now that's equal to 1 plus r. Raised to the 1 power, it stays the same. So what that means is inside the parentheses, we want that to be 2. We're going to be doubling every hour. What that means for r is that we want r to be 1. Our rate is 100%. Because what that means is that if we're doing the 1 plus 1, then that will be 2, and therefore we're doubling. Now, you don't have to do this every time. As we get into the process of looking at when we're doubling, we know it's going to be 2. Okay, so what I mean by this is our equation is going to look like this. We're going to say our population of bacteria over a period of time is going to be equal to, what was our initial amount? It's 100. And then when we look at our 1 plus r, that's going to be 1 plus 100%, which is 1, raised to the t. In other words, this is going to be 100 times 2 to the t, because 1 plus 1 is t. All right, let me pause there. Do you guys have any questions on how I was able to come up with this equation to model what's going on? I'll take that as a no. Now, what we're trying to come up with is we want to come up with a way that we can figure out when the population is going to go from 100, how many hours until it gets up to 350,000. And so I forgot 3 zeros there. Let's add that on. One more. Okay, 350,000. So what we're going to do is we're going to have 100 times 2 to the t. And we want to know when is that going to equal that. Well, guys, we don't know how to solve for t yet. You're going to learn how to do that, okay? And spoiler, it involves logarithms, okay? But we don't know how to do that yet. So how are we going to do this? What we're going to do is we're going to use Desmos to graph this, and then use Desmos to graph this, and we're going to see when they intersect, all right? So I'm pulling up my internet here, and let's drag this over. And it's going to take a little bit of a modification to get the right graph, but let's do this together. So I'm pulling up a Desmos here, and let's put in our first equation, which I think was 100 times 2 raised to the t, but we're going to let that be x. Let me hurry and check my work. Was that right? 100 times 2 to the x? Yes. Now we want to know when is that going to equal 350,000. So what I'm going to do next is I'm going to graph the horizontal line, 350,000. Now, when I go to graph this, obviously I can't see it yet. So what I'm going to do is I'm going to come up here to the wrench. That's your graph settings. We're going to change our window so we can see it. So the x's, we probably just need to go, I'm just going to go over to 25, okay? For the y's, though, we're going to need to go up to like 400,000. And now we can actually kind of see what's going on here. Okay, so this red graph, this is showing us our cells, our bacteria here, and it's doubling every hour. We only started off with how many? With like 100, and it's doubling every hour. How long until it reaches 350,000? Well, if I just click there, I can see it's only 11.7 hours. Less than 12 hours, and that went from 100 to 350,000. That is scary right there, right? What that tells me is you need to wash your hands and sanitize and wear a mask, okay? All right, so coming back here, let's write that. So the time is equal to 11.7 hours. That's how long it would take to go from 100 to 350,000. And then just to confirm my work, here's the key. And are we getting the same thing? Sure. This is just a what's it, a graph from the book, okay? And it's showing there's the intersection. That just shows we did it right. Okay, cool. So do you have any questions on how we did this right here? Now, one of the questions that got asked on the Friday lesson was why there was a preview for the movie Contagion on here. And it was because usually when I introduce exponential growth, I would show that because it talks about it. If you've seen Contagion, or if you haven't seen it, it's about basically a virus that spreads around the world that's infecting people at an exponential rate. So there's a part in the preview where guys like started with 1 and then 2 and then 4 and then 6, and in a month that's 3 months, that's 1 billion people or something like that. And so I'm like, see, this is a great example of exponential growth. Didn't really show that because basically we're living it right now, right? With this coronavirus, it's crazy, especially in you, like our rates are going up at an exponential rate. It's crazy. So I didn't really need to talk about it because we're living it. Okay, let's keep on going. I haven't heard any questions from you guys. So if you do have a question, please stop me. Now, what we're going to talk about here is radioactive decay. And this is where people kind of like freak out. They're like, this is too complicated. It's really not too bad. When something is radioactive, it doesn't mean that it gives you superpowers, okay? What it means is that it's changing, all right? So just think of it like that, okay? Let's go through, I'm gonna read through this paragraph and we're gonna highlight any key information. And then I'll show you how to do a simple radioactive decay problem. All right, exponential decay functions model the amount of radioactive substance present in a sample. The number of atoms of a specific element that change from a radioactive state to a non-radioactive state is a fixed fraction per unit time. This process is called radioactive decay. And the time it takes for half of a sample to change its state is its half-life of the radioactive substance. All right, so maybe you've heard of carbon dating. Carbon dating is a method that scientists have found to be able to go and look at something and say, hey, how old is this artifact that we found? And it's based on the fact that there's two types of carbon. There's carbon-14 and carbon-12. Carbon-14 is radioactive and carbon-12 is not. And what that means is if they look at the amount of carbon-14 in this artifact, it's decreasing at a certain rate, whereas carbon-12 is not. And so if they look at the level of carbon-12 to carbon-14, they're able to use models to kind of estimate how old that artifact is. So it's interesting. Anyway, let's do a simple project or a simple example, okay? Suppose the half-life of a certain radioactive substance is 20 days and there are 5 grams present initially. Find the time when there will be 1 gram of this substance remaining. All right, now I always think it's helpful to draw this out. So to start things off, we had 5 grams of this radioactive substance. And this radioactive substance is it's losing atoms that are not radioactive anymore, okay? So it's decreasing the amount of radioactive atoms. Now, its half-life is 20 days. That means, so this is at time 0. If I jump to time 20 days, how much is left of this radioactive substance? And it would be half of 5, which is 2.5. Well, then if I were to go 20 more days, that would put time up to 40, right? How much would be left? And that would be half of 2.5, which is 1.25. Well, if we were to go 20 more days, it's going to cut it in half again. So that's going to be 60 days. Now it's at, I want to say that's 0.625. Yeah, that sounds good. Now we're asked to find how long until it gets to just 1 gram. Well, looking at this model that we've come up with, we know it's going to be somewhere between 40 and 60, right? Because that's when it went from 1.25 down to 0.625. So we're trying to figure out exactly when it's going to have 1 gram left of this radioactive substance. Now, this little model that we drew here, they kind of help, or this little like chart here helps us get an idea of what to expect. But to get the full answer, we're going to need to do build a model here, okay? So first off, what we're going to do is if it's doubling, what does that mean our rate is? Go back with me. When we were doubling, what does that mean our rate is? It was going to be 2. Now, if we're doing a half-life, what does that mean our rate is going to be? This is where you should say it would be 1/2. I hope you would say that. But if you have a problem seeing that, well, why don't we just go through an example here, okay? So, for example, so I'm getting a new color here. Good night. let's look at just this first 20 days, okay? So if I start out with 5 grams, and we're going to go for 1 half-life, which is 20 days. But that's going to be, we're measuring this in terms of 1. That's 1 half-life, okay? How long until it takes, or what would the rate be to get it to 2.5? So I'm going to subtract that over, and I'm going to get, or divide that over. And 2.5 over 5 is 1 half. So what I want my base here to be is I want this to be 1 half. If we're doing half-lives, we want our base to be 1 half, okay? Hope that makes a little bit of sense. So now when I write my model, I'm going to see, okay, our population is over a period of time is going to be based off of our initial amount, which is 5 grams, and our base here is going to be 1 half because we're measuring it in terms of half-life. Now, the one other tricky thing here is we don't want to measure our time in days. We want to measure our time in terms of its half-life, which is 20 days. So we're going to take our time and divide it by 20. And the reason is because we want basically one of these units of time to be a half-life. And so for each day that I plug in, it's going to be, so like on day 10, that's going to be half of the first half-life. If I go into day 20, then that should be 1 half-life. If I do 30, that should be 1.5 half-lives. So that's going to be something you're going to get in the habit of, is when you're dealing with half-lives, let your exponent be divided by your half-life length, so that when you plug in days or hours or whatever, it's going to be it'll be 1 full half-life when you plug in that length. I hope that makes sense. Let me just finish this example and I can re-explain it. All right. Okay, so here's our equation. Our initial amount is 5. It's decreasing. We're looking at the half-life, so our rate is like -50, right, percent. So our rate is 1 half, and it's going to be our exponent we're dividing by 20. Now, what we want to figure out is when is that going to be equal to 1. To do this, we are going to graph this guy, and then we're going to graph 1, and then we're going to see where they intersect. So I'm going to go and pull up my Desmos again. And I'm actually going to refresh this guy because we are not going to be measuring nearly as high as before. So let's just get a new screen. And so the first one we said it was 5 times 1 half raised to the, now we've got to be careful, I remember it's x divided by 20. So that's representing our the amount of radioactive substance that's decreasing. We want to know when it goes from 5 grams to just 1 gram. So I need to put y equals 1 in there. And there we go. And on this one, I can actually probably just scroll along right here. You can see it's getting closer and closer. And okay, somewhere right here it went down and it looks like it's right at 46. 46.439. That's where these two intersect. So what does that mean? This is going down it's going down every 20 days, it's cut in half. And then cut in half again. And so after 46 point whatever days, that's where it's going to exactly equal 1. And it was 46 point, let me look at this, 43. Is that what we came up with? So our answer here is that after 46 point, I'm just going to say 4 days, this becomes 1 gram. It went from 5 to 1. Okay, cool. I'm going to pause that for a second. And I'm going to look at you guys and you tell me, does that make sense? Or do you have questions? Do I need to re-explain anything? No, I didn't hear anything. So are you guys good? Are you awake? You live? All right. I heard something. You're still live? Okay, cool. Or did you say barely? I don't know if I like that. All right. Okay, we're going to do actually just one more problem, guys. You made it to our last one. And actually, you guys kind of lucked out because normally I would teach you how to do regression. And that means where you're given the data, you basically use your calculator to figure out the curve. But you guys don't have calculators like to do that. So we're just going to skip it. So you guys kind of lucked out a little bit. But anyway, we're going to do one more. It's going to be a different context, but it's going to still hold true to what we've been learning about, okay? All right, so let's talk about this. Scientists have established that atmospheric pressure at sea level is 14.7 pounds per inch squared, and the pressure is reduced by half for each 3.6 miles above sea level. For example, the pressure 3.6 miles above sea level is 1/2 times 14.7, which is 7.35 pounds per inch squared. This rule for atmospheric pressure holds for altitudes up to 50 miles above sea level. Though the context is different, the mathematics of atmospheric pressure closely resemble the mathematics of radioactive decay. Okay, so let me talk about soccer for a quick second. So I'm a big supporter of Real Salt Lake, and hopefully you guys have gone to a game. One of the things that they talk about, not this season because we didn't do so well, but in previous years, we used to have a very strong home record. That means when we would play at home, we would almost always win. We were really good at home. And one of the advantages we had was the pressure, the atmospheric pressure. We were used to playing up in the mountains, right? Whereas when we played teams from California, they're used to playing at sea level. Well, as you go up in your elevation, the air kind of thins out. And so when people would come here, they would like get really tired. They're like, the air is just thinner. I'm not getting the oxygen I need to play as well. And we're like, we're used to it. So it gave us a great home field advantage. And maybe you've experienced that before, like when you go hiking in the mountains and you're like, oh, I can't breathe as well up here. It's because the atmospheric pressure isn't as high. It gets thinner as you get up higher in elevation. So I hope that makes sense. Now, what this is telling us here, let's highlight the key information that we're going to use in this next part, is that the half-life here, it's reduced by half for each 3.6 miles above sea level. So that's kind of like our half-life, but now instead of it being a time, it's going to be a distance, okay? Now, the initial value here is going to be 14.7. All right, so let's kind of make that same kind of chart I did before. Let's talk about the pressure at different elevations, okay? So when we're at sea level, that means we're our elevation is 0, right? We're 0 feet above the sea. The pressure is 14.7 pounds per inch squared. Now, what we're going to do is go up 3.6 miles. So if I go up 3.6 miles, it's going to cut that pressure in half. So now that's going to make it 7.35. And then we could keep going here. If I were to go one more, so I'm going to go up to the distance is now 7.2 miles. Well, now it's cut in half again, which is going to make it, I have this written down because I don't know that, but it's 3.675. All right, now the question says, find the altitude above sea level, also known as elevation, right? At which the atmospheric pressure is 4. Well, we just based on the chart we just made here, 4 is going to be somewhere between these distances because it went from 7.35 to 3.675. So probably closer to that 7.2, right? So we're trying to figure that out. So to do that, what we need to do is come up with an equation and then graph it and then see when it's 4. Now what I want you guys to do is based off of what we did on this last one. Here was a model we came up with here. see if you can come up with the equation that models what's going here on here. It's still a half-life problem, even though it's dealing with distance instead of dealing with time. So I'm going to give you 30 seconds, see if you can come up with the equation. All right, is there anyone who wants to share what they came up with? I promise I'll be nice, even if you're wrong, but anyone share what you came up with? Go ahead. I'll call on someone, guys. Don't make me. All right. Micah, I'm calling you out. What did you come up with, Micah?
I don't know. I'm still working on it.
Well,
Still working on it.
that's all right. Well, help me out here. Okay, so what is our initial pressure?
14.7 pounds per inch.
And what is our, if we're doing a half-life problem, what is the base of the exponent going to be?
1/2.
Yeah, just like in our last example, it's going to be 1/2. And I'm going to put it in parentheses so I remember that. Okay, now when I go to do my exponent, I need to remember to put it in terms of its half-life. So it's not just going to be in the distances, right? The D is for distance here, not days. And the P is for pressure. Anyway, Micah, what's our half-life?
3.6 miles.
So I just make sure I divide by 3.6, and boom, guys, that's the equation. We've got our initial pressure. If it's being cut in half, then our base is going to be 1/2. And then our exponent, just make sure on those half-life problems that you divide it by 3.6. There you go, that's it. Now, what I'm going to do is I'm going to graph that and see when it's equal to 4. Okay, so I'm going to, last one here, pull up Desmos. Where are you, Desmos? Here we go. And I'm going to change it. And I might need your guys' help to tell me what to put, but I think it was 14.7 times 0.5 raised to x over 3.6. That's wrong, yell at me. And then here we're looking at when does that pressure get to 4? What is that pressure going to be? Yeah, what is the altitude with the atmospheric pressure is 4? Okay, cool. So I need to make that y equals 4. And let's see where those intersect. I'm going to have to come back a ways here. And okay, there we go. Looks like it's right here. So this says 6.76. So if I go up 6.76 miles, that's where the atmospheric pressure is, 4 pounds per inch squared. Now, does that match up with what we're saying here? We said it had to be somewhere between 3.6 and 7.2. And we got that it was 6.76. Let's just say that. So the distance we would have to go up here is 6.76 miles in order to get the atmospheric pressure of 4 pounds per inch squared. All right, so these problems, they're a little complicated. They're probably new, but I've shown you a couple of examples. Do you have any questions on these examples before I basically let you go for today? I'm going to stop sharing my screen for just a quick second here, because I need to just take a quick, I want to hurry and like copy who's here so I can take, it's kind of like how I'm take and roll. Just get an idea of who's tuning in. All right.
So, Mr. Solberg,
Yes,
sorry.
Andrew.
So when you put it in the calculator, do you put in the 5 times 1/2 to the exponent, or is it just you do put in the exponent, right? Sorry. I'm like,
Yes. So when I put it to Desmos, let me pull that up here. I put in like the 14.7 times 0.5 raised to the x over 3.6. So you need to put in that whole thing. Is that what you're asking, Angelina?
yes, I think I saw the 0.5 and then I forgot that it was supposed to be 1/2. Yeah, okay, that makes sense. Sorry. It was just a visual thing. Okay, thank you.
Thank you for asking the question. Okay, so here's what I'm going to say. If you guys do have questions, you can stick around and we can talk about them if they're from last chapter, this chapter. But let me just say thank you for tuning in. I got like 15 of you guys, and that's awesome. So good job waking up on a Monday morning and doing what you need to do. I put your assignment on Canvas. It's kind of not as nice and neat as the other one. You kind of basically just need to copy the problem down to a different piece of paper. It's kind of jumbled together. Skip number 44 though, because that was one of the regression ones that I'm not going to make you do. So the assignment's there. When you come back, your project is due on Tuesday, December 1st, and then you're going to have a quiz. So please do your homework. Enjoy your break. Stay safe. And if you have questions, just stick around, okay? Thanks, guys.
Thank you. Happy Thanksgiving.
Happy Thanksgiving to you as well. Thank you.
Mrs. Solberg.
Yes.
So, I just had a quick question. So, if the equation is going to be growth, you add a 1 to the rate, correct?
Correct.
And then if it's decay, you minus the 1 from the rate.
So it's kind of like it'll be more like 1 minus the rate. So if I go back with you here, let me hurry and just share my screen again. Maybe I didn't show that as well as I should have before. So let me excuse me. When we learned these equations in 1050, let me go back to where it was. They show this equation here. Instead of a plus, it's a plus or minus. And so it's plus the rate when it's going to be growth, and it's minus the rate when it's going to be decay. So for example, when we did this problem here, it was 0.9858, which meant we did 1 minus 0.0142. So the rate here is 0.0142, which is 1.42%, but that's decreasing at that rate. So it's like 1 minus that. That's how we got the 0.9858. Does that answer your question?
Okay. Yeah.
Awesome. Thank you for asking the question.
Thank you.
You're welcome. Anyone else have questions?
No, it's just too early for this. Thank you, Mr. Solberg.
Thanks for tuning in, Allie. Have a good break.
You too.
Thank you.
Thank you. Have a good break.
I have a question, but it's not on this.
Go ahead, Adam.
So I haven't been like doing the things for last week, and they're closed. But I was wondering if I could like still turn it in, or what? Like I didn't turn in like the Unit 3 homework submission and week 3.
Okay, let me pull up. Let's see what you're looking at. So you're saying you didn't turn in your homework for the last unit.
Yeah.
Well, Adam, why not, kid? Let's see. Here's the thing. I can open it for you, okay, and I'll let you do that. But the whole point of the homework is to do that before the test so that you're ready. Because really, in the end, your homework doesn't make like a huge impact on your grade, but it's there to help you get ready for your test. So I'm going to open it up to today, okay? So you can still go in and do that. What was the other thing you were saying?
It was the week resubmission.
Yeah, so with those, I'm going to like drop one of them or so. So if you miss a week, just start over. Like the week 4 is due today. Have you done the week 4?
Yeah.
Make sure you've done that and then just stay up to speed moving forward and you should be fine.
Okay.
Sound good?
Do I have to fill to redo the unit 3 test though? Is that right?
Will you say that again a little louder?
I said for the unit 3 test, do I have to like submit all the homework in Canvas to redo it?
That is a good question. No, so okay, so let me back up a bit. So you took the unit 3 test. How did you do on it?
I got what was it? It was like 9.5, I think, out of 13.
So not bad, but you're wanting to redo it. Is that what you're saying?
Yeah,
Okay,
because I'm pretty sure that's one of the things keeping my grade down.
gotcha. Okay, so what I'm gonna say here is when I'm trying to look at your quizzes. So what I'm more worried about are your quiz scores because there was I think there's 3 quizzes, a 1.2 quiz, a 1.3 quiz, and a 1.4 quiz. How did you do on those quizzes?
Let me look.
It looks like 1.4 you did great on, the 1.3 was not good, and 1.2 was not good.
There's one I got like one of those.
Okay, so here's what I'm gonna say. Wait, 1.2 analyzing functions quiz. This is saying you did good on it. Hold on, hold the phone for a second. Oh yeah, I think I was looking at the wrong person. Okay, so yeah, your 1.2 is good. The 1.4 was good. It's just the 1.3, and that was the one on like the transformations, I believe, or the parent functions. That's what that was. Okay, so what I'm going to do is for the 1.3 quiz, I'm going to have you retake that. And then for the homework, you're going to submit that. How much of the homework did you do?
I did pretty much all of it.
Okay.
I just didn't turn that in.
Okay, so give me 1 second so I can. Okay, so 2 things that you need to do. Number 1 is before you take that quiz, 1.3, I want you to go and like review it and look at what you did wrong. And if you have questions, email me and get help before you retake it or study your notes or do whatever so you're better prepared. Once you retake that and your score is better, then I want you to go and do some test corrections. So the problems you missed on the test, go through and like figure out why you missed it. Once you've done that, then I'll unlock a retake for you on the test. If you don't know what you did wrong, then you need to get in touch with me so we can fix your mistakes, okay?
Okay.
Does that answer your questions? Do you have any other questions?
I do not. I appreciate it.
Okay, you're welcome.
Have a good Thanksgiving.
You too. Thanks, Adam.